And I often have to have that conversation with companies and collaborators where they come and say, oh, can you model this alloy and tell me what the effect of this one element will be on this 15 element alloy? And the answer is, sorry, I can't, right? I've got to simplify it down to a binary or a ternary, and then I can tell you that behavior, and then we can extrapolate that behavior once we really understand it. And so it's not quite as simple as I'm going to put all my atoms in a box, run it through a computer, and out pops an answer that tells me what the properties will be.
Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out. And before we get started, just wanted to mention that we have released material science merchandise for those of you who want to support us or just express your passion for MSE. You can check out more of the designs at itsamaterialworldpodcast.com/shop or by clicking the link in the description. All right, let's get right into it.
Hi, everybody. We are excited to welcome today's guest, Dr. Alessandro Mottura, onto the show. Alessandro is a professor at the University of Birmingham, focusing on doing simulations at the atomic scale to better understand superalloys. Thank you so much for joining us today, Alessandro.
Thank you very much for having me.
Awesome. So we'll start with the basics. Can you quickly define what an alloy is and then tell us about how that's different from a superalloy?
Yeah. So many people have heard of what an alloy is. An alloy is basically a mixture of two elements that make a metallic material. So anything that has two or more elements in it that result in a metallic material, that is an alloy. And most metallic materials that we use in engineering applications are indeed alloys. Steel is an alloy. Obviously, aluminium alloys for your alloy wheels on cars, those are alloys as well. More advanced alloys like titanium alloys and the subject of today's talk, but also even jewelry, gold. Although you might be able to buy pure gold, when you buy jewelry made out of gold, even gold is actually used as an alloy of gold and something else in jewelry. So it's very common that we use alloys and not pure metals, because alloys do tend to have better properties for what we require. So we mix elements to achieve what we would like. So the next question you had is, how is that different compared to a superalloy? Well, there are two actual definitions of superalloys that I've heard. So I've heard people claim two different ways of defining superalloys. Some people say superalloys are just alloys that have got super properties. So they're alloys that are particularly high performing at high temperature in highly oxidizing environments, etc. Right? So that's one way of defining it. So it's about the properties. Another way to define it is about the fact that they're very complex. So a lot of people say a superalloy is basically an alloy that has got so many elements in it that is a superalloy. And in fact, if you look at the number of elements that superalloys have, when you normally talk about a normal alloy, you're talking about, for a steel, mixing 2, 3, or 4 elements. For a titanium alloy, again, 3 or 4, maybe 5. A nickel-based superalloy will generally have up to 15 elements mixed in. And I'm not talking about impurities. I'm talking about elements that are added in to specifically achieve certain properties. So I've used both in the past. So superalloy is either an alloy that has got special properties, super properties, or it's a very complex alloy. And both are true. So that's what a superalloy is.
What is the purpose of adding, up to 15 metals as additives? What does each of them contribute, like a certain property to the overall superalloy?
It's very interesting, because I think that's where a lot of research really focuses on, is to trying to establish what the role of all these elements are and how to mix them in the best way to achieve what you'd like. Some elements are added for oxidation resistance, for example, to allow these alloys to sustain or resist a more oxidizing environment. Others are added to convey more temperature resistance. Other elements are there to make the material lighter, maybe, or to try and stop it from being from being too heavy. Other elements are there because depending on the microstructure, you may need to have a specific type of behavior in terms of different mechanisms that happen inside the material. So there is many different reasons. Oftentimes, one element will be positive for one of these reasons and negative for another reason. So it's about balancing all these alloys together to find the best properties. Other elements may be added actually not for the properties of the alloy, but for the properties for the manufacturing ramifications. So it may be simpler to manufacture an alloy if you add a specific element to it, which then might not have really an effect on the properties, but it's there to aid the manufacturing. So that is the case of some elements in aluminium alloys are added in order to make the melt more fluid so that it can be less viscous and flow into the cast better. So yeah, many different reasons. And the key, I think, the magic is to find the right balance. And nickel-based superalloys are predominantly nickel. And then there are some other alloying elements that are added in significant amounts, like aluminium, for example. And then there are other elements that are added in very minor amounts. And those are either because just those minor amounts is what you need, or because they might be very expensive. So there is also a cost concern sometimes in some of these elements. So yeah.
Yeah, so you just described a really complex process where all these little elements play such important roles to make up the overall composition of a superalloy. So how did we get to our first superalloy? It kind of sounds like you had to do more than just guessing at this point. How were we able to work onto it?
Yeah, early on, I think it was very much guessing. I think the nickel-based superalloys came about because right after the Second World War, people started using a lot more advanced engines. Basically, it was engines that were turbocharged, or they started really using jet engines, for example. And so quickly people realized they needed an alloy that really was able to work at very high temperatures. And the choice of nickel was just driven from the fact that nickel is a common element and it's got a very high melting temperature. So that's why people quickly settled on nickel as a base element. And then they started alloying with different elements to try and get the properties they require. And it was very much a trial and error process. Sometimes that trial and error was driven by some theoretical knowledge. So for example, in the 80s, people started playing with the concept of adding an element called rhenium in place of an element called tungsten. And the reason why they played with, they tried that was that rhenium is slower diffusing than tungsten. And so they thought that by adding rhenium, rhenium is very close to tungsten on the periodic table, so it probably has the same effect on the property of the alloy, but because it's slower diffusing, it may even give better high temperature properties. And so that's why they tried rhenium, and they tried a little bit and it worked. They tried a little bit more and it worked. And they kept adding until they realized that adding too much wasn't so good. So it was very much trial and error very early on. And so it's taken quite a long time to get from a relatively basic alloy that only perhaps had 2 or 3, 4 elements in it to what we now call a superalloy that has got 15 elements in there. Yeah. And oftentimes the changes in compositions are not just due to the fact that you discover that an alloy has got particular properties, but you may have a constraint that you impose in terms of, say, for example, the microstructure. You might want a single crystal-based superalloy. So a single crystal-based superalloy started to become more common. People had to redesign the composition so that it was more appropriate for single crystalline applications. And another aspect to consider is that sometimes the composition is driven by cost, by supply chain, and by world conflicts. And so again, you have to keep adjusting your composition because something else out of your control may be changing the cards on the table. And so you might have to reduce the use of cobalt, or reduce the use of tantalum, or ruthenium is just too expensive, and so you don't want to use that, and so forth. So there is different things at play that mean that you have to keep changing the composition to try and achieve what you'd like.
So is that why there are different types of like base super alloys? Like I remember there's nickel based, cobalt based, even iron based. Is that a primary driver in that?
That's certainly part of it. I think I mean, when you talk about the different bases, you often have such distinct properties that that you cannot really easily swap from one to the other. I.e., in a jet engine, you cannot just take away nickel-based superalloys and use iron-based superalloys or cobalt-based superalloys. So it's a little bit more more complex than that, I think. But I think certainly you try and have people always think when you think of materials, and I think this is very common, that you try to make all your properties better. In reality, you can never do that. A lot of the properties are in conflict with each other. So you're trying to get the balance of properties that you need for a specific application. And so you'll always try to aim for that balance, and different alloys will be tweaked to achieve the right balance for a particular application. So an alloy is just absolutely the best choice for that specific application. And inside the kind of technology that these alloys are used for, like jet engines, it's kind of fascinating to think that actually you don't just have one type of nickel-based superalloys in it. Within the jet engine, you use many different types, because each type will be tailored for exactly that component in exactly that part of the engine, because it will see a specific type of temperature, specific stress, specific oxidizing environment. And so all of these materials will be tailored for very specific applications.
And so going back to what you just said is that as material scientists, I think it's important to understand material selection could be a very large role of whatever we do. So when we talk about a system so complex that there's 15 components, there's not really enough time in the world to try and tweak each individual one. So coming from an academic point of view or industry point of view, how do we go about such a complex system and tweaking them to get the properties that we desire?
So traditionally, this is done by basic knowledge of the periodic table, basic knowledge of what's been tried before, and some trial and error. And with every trial and error, you try and assess why something has failed, so that might inform what the next step is. So rather than blindly trying all possible different arrangements of all these compositions, all these elements, you will try and guide your discovery by using the information you have and by kind of charting your way forward in an intelligent way. Now that is the traditional way to do it. Another way that is perhaps looking forward into the future is to design these alloys from the bottom up. So there is lots of new developments with modeling tools that allow us to predict how a particular element might affect the properties of a material, to predict how a composition will behave. And there is lots of advances in data science and artificial intelligence that can help you guide that process as well. So I think there is now a bit of a paradigm shift from the traditional way of developing alloys, which is very much based on trial and error kind of back chemistry, to a more focused, more data-driven, more simulation and theory-driven one that will allow you to hopefully get an answer much, much quicker. And again, I think where there is a space for that new approach is the idea that you want to tailor a particular alloy to a specific composition. So whereas now, as a mechanical engineer or an aerospace engineer designing a jet engine, you'll kind of have to pull from a library of X number of alloys. You have some alloys at your disposal that have a range of properties. You'll pick the most suitable one. Mm-hmm. Perhaps someday in the future, we'll be able to actually say, well, actually, I need an alloy with specifically these properties. And get something tailor-made. So that would be the holy grail, I think.
For sure. And so you mentioned this jet engine application multiple times. So what materials were previously used, and what kind of advantage do superalloys provide in this specific application?
So I think the nice thing about the application of jet engines, I think jet engines and nickel-based superalloys are in symbiosis, essentially. I don't think jet engines would have ever become a thing unless nickel-based superalloys were around. And I don't think nickel-based superalloys would have become a thing unless jet engines were around. So jet engines, just I guess for people that do not know much about jet engines are basically sucking a lot of air from the front of the jet engine. Some of that air gets compressed to very high pressures into a combustion chamber. And then there it gets mixed with fuel, it ignites, and then those hot gases then expand through the turbine section, which is at the back of the engine. And by expanding through the back, it makes the blades and the disc holding the blades turn. And those blades are then linked through a shaft all the way to the front and allow the fan and the compressor to pull in even more air and compress even more air. So in that way, it's very similar to any combustion engine. You're basically compressing air, you're mixing it with fuel, you're igniting it, and then you're using that work done by that hot gas to obtain work out of that hot gas. Now, where it's different from a car engine, for example, is that a car engine is reciprocating. So you've got a piston going up and down. And so your burns are discrete. You'll have a bang, right? Whereas in a jet engine, you have an engine that keeps rotating and your burn is continuous. And because of that, it can be much, much more efficient. So when it comes to flying around the world in an efficient way, then jet engines are really the only answer that we have at the minute. And so that's why jet engines were so important. So I often, when I talk about jet engines, I kind of tell people about how it was to fly back in the 60s, 50s and 60s. Say, for example, I think that the first flight from London all the way to Brisbane was sometime in the late 50s, early 60s. And it was a propeller plane. I think it was 1954, 1956, something like that. It was a propeller plane. And it took about 12, 14 days to fly from London all the way to Australia. And you had to have something like 20 stops. Which is significant, including a train ride. so if you flew from London to Brisbane, you had to actually land in Paris and take a train ride from Paris to Brindisi in the south of Italy, and then fly the next leg that was Brindisi to Cairo, I think it was, something like that. So that was flight back then, and that was because you had propeller planes that utilized normal combustion reciprocating engines. Then jet engines came about, and all of a sudden, in a space of not very much, 10 years, you had a complete transformation of the industry. And you went from taking 12, 14 days to taking 48 hours. And then with still some stops, granted. And then that was further reduced to what it is today. I mean, today you can fly from London to Brisbane in one leg. If you it's not done for economic reasons, but technology is there. You could do it. Mm-hmm. It would take you about probably 14 hours. And it wouldn't be that expensive to do that. And you could do it without refueling the plane. And all of that is thanks to jet engines and thanks to the fact that jet engine efficiency has increased massively. We're talking about, I think, the first jetliner, I think it was the Comet, would use about, I think it was on the order of about something like 15 liters per passenger per 100 kilometers of gasoline. And planes today that are coming up, that are the most efficient planes, you're talking about 2 liters per passenger per kilometer. So a massive improvement. And that is all thanks to jet engines and thanks to the fact that in any engine, basically, the hotter you can make the core of the engine, the more efficient the engine is. So this goes back to a thermodynamic cycle. So if you've done thermodynamic cycle and covered them, you'll know that the pressure ratio and the temperature ratio between the outside and the atmosphere and the gas that you're compressing, essentially, is what drives the efficiency, is what controls the efficiency. No, we cannot change the temperature of the outside atmosphere. That is fixed. But if we increase the temperature inside the jet engine, then we can make our engine much more efficient. And so that is what drives the development of these alloys, is to try and make the inner core of the jet engine even hotter. And we are at that point of that design where essentially the gases inside the jet engines are hotter than the melting temperature of the alloys themselves. And so, the kind of analogy that is often pronounced in this circumstances is like, it's like having a pump that is made out of ice, and you're trying to pump hot water through this pump made out of ice, and you're expecting it not to melt, right? So that is the kind of design challenge. And so we do a lot to try and make them not melt. So I've actually got some props here. I know some people are just going to listen to the podcast, but I've got a portion of a disc, of a turbine disc, with the jet engine blades slotted onto them. And this is quite heavy, actually, to lift up in front of the camera. But this is an example of how the blades, these blades are single crystal blades. They're made so that they can sustain the highest temperatures, are slotted onto the disc. And the disc is actually a polycrystalline material, because we don't need the additional temperature capabilities in the disc itself, right? And so what you might be able to see in the video is that there is holes at the bottom here, and these holes are a way for cold air being blown into these holes, and that cold air essentially ends up in the blades. And if you look very closely, you'll see little tiny holes at the starting edge of the blades. Hopefully they're visible, and those tiny holes essentially are blowing up cold air as you're running the engine. Now, cold air, again, it's interesting. We talk about cold air. Cold air, as far as a jet engine designer is concerned, is about 700 degrees C, right? Sorry, I know you're an American audience. You'll have to do the conversion to Fahrenheit, but it's really hot, right?
Yeah.
So that's how we can avoid them from melting. And in fact, these blades are hollow. So inside it, they've got like cooling channels. So this is a blade that is sectioned. You can see that it's hollow, and there is essentially cold air, i.e. air at 700 degrees C, flowing through this and coming out the tiny holes at the running edge. And you can see this blade is actually white. So this section here, you can see it's white. And that's because it's been coated with a ceramic, and that gives us a little bit extra temperature capability. This is akin to, say, a baked Alaska, right? If you're baking a baked Alaska, you cover it with some meringue, and you're expecting the ice cream not to melt in the oven. And that's exactly what we do here. We coat it with a ceramic, which has got much higher temperature capabilities, but it's not good with mechanical properties. This way, we are expecting that layer, that very thin layer of ceramic, to give it an extra little bit of protection. And again, this is all to increase the temperature inside jet engines. And the more we increase the temperature, the more efficient the engine is. So that's what very much drives the development of these alloys, is to try and get to a higher temperature inside the jet engine.
Yeah, so one thing I want to ask is that you're saying that the larger temperature gradient we can create, more efficient we get. But I'm sure other people have the question, does that also mean we're going to go faster? And I just happen to also know about jet engines is that there's basically a maximum limit of speed we can get until we hit turbulence. Like we create like an uneven waveform within like the wake that we make. And so it's actually ideal that we go below that or above it. And above it so high that we can't get to it. So can you talk us about what these super alloys are doing to make it more efficient and how that doesn't affect the speed of the plane?
So, you're right that you cannot really go. Every engine will have a specific range in which they're more efficient than others. So in the case of jet engines, yes, you cannot really have an airflow that is too fast. If you want to go faster than that, then that's where you have to start using afterburners, and you start having to use other types of engines that are then more efficient and allow you to get to much higher temperatures. So the air inside the jet engine, I don't know what the speed is, but actually it isn't that fast. So what often people think about is that what actually makes a jet engine works is that you're pushing air through the back, and that is what provides the thrust. And so you've got to push the air as fast as possible so that you can fly further, right? Or faster. In reality, in a civil jet engine, you see a big fan at the front, right? And that fan is going to suck in a lot of air. I think people often talk about squash courts in seconds, right, of air. So if you play squash, you have a kind of idea of how big a squash court is. So you're sucking in all the air. Majority of the air actually does not go inside the jet engine. Majority of the air bypasses around the engine, and only a tiny fraction, like about 10%, goes inside the jet engine, gets compressed down, goes through the combustion chamber, ignites, and then expands to the back. And as the air expands, you're basically taking work out of that gas as much as possible so that you can drive the fan at the front. So ideally, in a perfect world, the air blowing out would go out at no speed, or very, very little velocity, essentially, because you're trying to get as much of that from the system so you can drive the fan at the front. And the fan at the front is designed to try and move as much volume of air as possible at lower speed. And if you can do that, that's more efficient. So some of the most modern concepts of engines involve having very big fans at the front that are actually driving slower than the rest of the engine, and they've got a gearbox to try and slow it down because you want to run it in the most efficient range, essentially. And so there is an engine currently developed by Rolls-Royce that has got this arrangement with a fan at the front and a gearbox that allows that fan to spin at a slower rate. And that gearbox is a monster of a job, because it has to, I think, the power going through that gearbox is equivalent to a whole grid of Formula One cars at that start. I think that's the kind of thing that usually people say as an anecdote of the kind of horsepower that is driven through this essentially mechanical device that is, maybe about this big, right? Oh, maybe a bit bigger, but something that you can definitely look at up close, and it's not too big. Yeah. So that's so you're really not trying to maximize speed here. You're trying to maximize efficiency, at least for civil aviation. You really you don't want to get too close to the speed of sound. You want to stay somewhat off from that, and then try to make your flight as efficient as possible.
And so I guess another question we had was that we kind of talked about the material selection and how we ideate and build upon superalloys, but how long would it take if we found this new novel form of superalloy that we want to put into a jet engine? How long does that take? And what type of improvements do we see? Is it very 10-year improvements, 20-year, 5 years? What does that look like?
I think it largely depends on how big an issue you're solving with your magic composition, right? Certainly, I mean, you have to imagine that an industry like the aviation industry is relatively conservative in that it doesn't like to try new things unless they're proven, simply because you don't want to have catastrophic losses of aircraft, et cetera, et cetera. So whenever you're talking about something new, the immediate question I guess I would ask is, how new is it? An evolvement of something that just already existed, so we already know the technology, or is it something entirely new that we have no idea about? So that's one aspect to consider. The other aspect to consider is what problem you're solving. How pressing is that problem? Right? Because if it's not that pressing, then of course it will take longer. If it is, for example, a small tweaking composition that solves a massive problem that the whole industry is trying to solve, then you could imagine that kind of speeding through and going into service quite quickly. If you're talking about a massive change, a whole new material system, basically, that might give you a marginal improvement in efficiency, then you're probably talking maybe not even maybe it will never come to actually come into service. So it really depends. But I guess if you're talking about something that is a significant change, you're talking about decades, because if you, let's say I find that I can add to the alloys that are in these blades, I can add something like titanium or some magic element that I kind of put into it, and it makes this blade behaves much better. Mm-hmm. Then I might have discovered that and I might have made simulations based on that, then I'll have to kind of hand it over to someone who will be able to then mix that alloy and get some samples to actually test that I was right. That might take a year or two. Once that happens, then there will be lots of people that will try and understand, why is this happening, right? So that takes, you cannot just do something and see it works and be done with it. You want to understand why it works. And so that might take a few years, at least to have a basic idea. And once you do that, then you want to try and actually manufacture stuff, and you want to see whether it has an effect on the manufacturing. And so that takes a few years. And then once you've sorted it out, you're essentially ready to move up to higher TRLs, right? Your technology readiness level scale, you're ready to go further up, and you're ready to perhaps start making some components. But again, scaling up brings a whole sorts of issue that you might have to solve. And depending on your material, you might find that it takes quite a long time to really nail the particular manufacturing process that you need to make your component. And so all these stages will take time. So it can be anywhere, I think, from 10 years to 30 or 40 years. And once you actually got there, then you've got from there to actually have it done routinely and have that part in a jet engine that is many jet engines around the world are using that same part made out of that same material. That takes some time, because companies will not just be worried about the properties that a part delivers, but how efficiently they can manufacture it, the cost of that part, and a whole other things that are outside of the control of the technology itself. In a way, you might have this wondrous material that you just made, but if it cannot be made reliably, if it cannot be manufactured in a way that your company or the company you're working with is happy to use it, if there is no supply chain for it, then it's never gonna go anywhere. So there is definitely lots of other pressures, but yeah, you're talking about decades.
Wow. That's crazy that it's such a long horizon for this whole design roadmap. But bringing it back to the basics of superalloys, you mentioned this balance of properties with alloys in general, and that's something I learned in my class last year. So even with steel, it's like low carbon versus medium carbon. You're giving up like your strength to ductility ratio. But one thing that I remember about superalloys is you kind of have like the best of both worlds. What exactly about the structure of superalloys gives it those properties?
Well, that's a good question, I guess. I think one of the special thing about superalloys, nickel-based superalloys, is that they have what is known as an anomalous yield behavior. So normally all metals, all alloys, you'll be able to bend them, right? The nice thing about alloys is that they yield, right? You can take a bar of an alloy and you can bend it and it bends, and that's something that you want, because that kind of yielding behavior that allows you a number of things. The first thing is that it allows you to manufacture things more easily. It gives you malleability. So if you were to forge things, you can actually forge them. Or cold work them. But also it allows you to have a material that does not fail in an uncontrolled manner, right? So the nice thing about alloys and superalloys is that they don't break in a sudden way, right? Or less sudden than, say, a ceramic mug, right? So you wouldn't want your blade to just rupture without any prior warning. You'd like it to deform in a controlled way that you can predict, basically. And that's why we want yield. We want these materials to be able to yield and deform. And most alloys, and that's why we pick alloys for these kind of applications. The problem with most alloys is that they tend to yield a lot quicker as you increase the temperature, i.e. their yield strength will generally drop with temperature. And that's not good, right? It's kind of obvious why that happens. If you can imagine, like as you get closer to higher temperatures, you get atoms kind of vibrating around faster, moving faster, and that allows these locations and the mechanism that leads to the formation, all those mechanisms happening quicker. The wonderful thing about nickel-based superalloys is that they have an anomalous yield behavior, which is that essentially they get actually stronger with temperature up to a point, but they get stronger at higher temperature before they lose that their strength at a higher temperature. So that is what is really wonderful about these materials. They're more capable at higher temperature, and that is all down to their microstructure. Every alloy will generally contain multiple phases. I'll have to explain this for the audience a little bit, I guess, but phases are basically an area of a material that has got homogeneous properties, right? So when you thinking about a material, you can think about the material having a state. And so it can be in the liquid state, gaseous state, solid state. But then within a state, you may have material existing in multiple phases. And phases are nothing but just basically area of that material that have got different properties. So inside something like nickel-based superalloys, you generally have at least two phases. And it's the particular combination of those two phases that really gives these alloys its behavior. That is true not just of superalloys, it's true of a lot of different alloys. You generally, in more advanced alloys that you can think of, you generally always have two or more phases, because you can kind of get the best of both worlds, basically, right? By combining the properties of multiple phases. And so in nickel-based superalloys, the combination of these two phases allow us to have this anomalous yield behavior. One thing that is kind of really I really like about nickel-based superalloys, particularly the single crystalline type that makes up the blades that I've shown earlier, is that if you look at them under a microscope, you'll find a microstructure that is made of what I call bricks and mortars. So you'll have essentially bricks of one phase surrounded by the second phase, which is the mortar phase. And that combination is what really gives us that high temperature capability that we require out of these alloys.
And so you mentioned this idea a little bit before in this episode. And so a new development with superalloys is the idea of just designing them from the bottom up. And so we were just wondering, what is the scientific basis behind that idea, and what could it lead to in the future?
So, well, it starts, I think, with quantum mechanics, I guess. We know, we can predict how elements and atoms of those elements will interact thanks to quantum mechanics. We've got tools that allow us to use approximations to solve Schrodinger equation to try and predict what the behavior might be. And so that's where it starts. You're basically trying to use tools like that to predict what the behavior of your alloy might be. The problem with doing that is that it's very computationally expensive, right? So you cannot easily do that for a complex alloy. You certainly cannot do that for 15 elements, right? So in my research, I use simulations, quantum mechanical simulations, to predict how elements behave. And I often have to have that conversation with companies and collaborators, where they come and say, "Oh, can you model this alloy and tell me what the effect of this one element will be on this 15-element alloy?" And the answer is, sorry, I can't. Right? I've got to simplify it down to a binary or a ternary, and then I can tell you that behavior, and then we can extrapolate that behavior once we really understand it. And so it's not quite as simple as I'm gonna put all my atoms in a box, run it through a computer, and out pops an answer that tells me what the properties will be.
I wish.
Yeah,
I wish.
That would be the obvious future. Well, the problem though is that it cannot even be happening in the future, because the kind of theories that we have, for example, the quantum mechanical theories that we have, the ways that we solve these equations using approximations, means that the computational time scales with the number of atoms cubed, right? And so if you can think about that, you immediately can realize that even if you just increase, you go from simulating 10 atoms to simulating 100 atoms, you suddenly have a much, much longer simulation, and you cannot really go up to 1,000 atoms. And so we know we cannot use these tools. We will not be able to use these tools in 10, 20, 30 years, no matter how much more powerful the next chip from Intel will be, right? It's just not going to get us there. And so we have to find ways of upscaling our methods and to try and solve bigger problems by having the same type of accuracy and understanding we get with quantum mechanics, but on a bigger, more complex system. And I guess there is a lot of space there that is still under development. So obviously, there is a lot of people that, for example, explore ways of doing this using lots and lots of data, using artificial intelligence. So you can imagine that you could, for example, use quantum mechanics to simulate how different mixes of very few atoms would behave, and use artificial intelligence to recognize a pattern and then give you an answer of what might be a better performing material for a specific application that is a more complex material that you've never simulated directly, but based on the information you have, that might be the answer. So there is lots of work in that space, but it's certainly not simple. I think at this point, a lot of people like to say that we are there, that we are doing it, and I think it is happening. There are companies, for example, and I know you have actually interviewed a company that works in this space. There are other companies also that do similar work, and they're very effective. But there is, I think, and I think they would say that themselves, there is lots of work that still needs to be done in order to achieve an objective of being able to just essentially predict precisely what a material, or how a material will behave, or find a better material based on some constraints that you face it. But I would imagine in a future, maybe in 20, 30 years, you would basically define the particular properties that you need. Those properties would be probably linked to some mechanistic behavior that is going on, that you can essentially code in an equation, and then you'll then try and tweak your composition to give you the specific mechanisms that you require to achieve those properties. But I think that's still a way a bit far. And also, again, you're not talking about just a complex alloy. You're not talking about just mixing 15 elements, but you're talking about them having them perform in an application, but also you have to make the material. And that often is something that people forget. You might come up with the best material in the world, right? But then if you can't make it, it's kind of wasted time, right? So it's difficult. And then the other aspect that I haven't really mentioned is that you might then make the best material in the world that has the best properties, be able to make it, but then it's not durable, right? It doesn't last in the application. And again, that's another set of problems. Or nowadays, then maybe it's not recyclable, or there's all sorts of other problems that might come up. And so it's a very complex, multidimensional problem that is not just the 15 elements that you're trying to tweak and achieve a result. There's lots of other things that come into play. So it's quite a lot that needs doing.
Yeah, Puneeth and I did a computational simulation class. I think it took 4 days to simulate just like 100 atoms of water for I think it was 100 picoseconds or something like that. So yeah, it's crazy how much more we need to do to understand more. But that's a really interesting way of thinking about problems. I guess moving on to other problems that are taking novel solutions is we talked about 3D printing with you before. So why is 3D printing being considered with superalloys, and what about it is beneficial over what we have now?
So I think there is quite a lot of hype about 3D printing. I think it has captured the imagination of people. This idea that you could have a printer at home and you could make anything that you needed, right? It's certainly something that's fascinating. I think what people don't realize until they actually get a 3D printer is how long it takes to make something. And so you have to imagine that relative to a traditional way of making something. I'm trying to think, let's say, I don't have a nice plastic bit, but let's say I don't know, let's say I wanted to make the plastic casing for this little dongle from Apple, right? If I wanted to print that, it would probably take me, I don't know, I don't have a 3D printer, but it would probably take me an hour, something like that, right? Whereas, you know, you could go to a factory that doesn't use 3D printing, and that factory could churn out millions of this every hour, right? I guess 3D printing has certainly a space in the manufacturing world, but you're really talking about using 3D printing in a handful of situations, particularly where you have low yield, high value parts. I think that is the best way of considering how you might use 3D printing. So in situations where you're not going to make too many parts, but these are going to be very expensive, and you want to easily be able to tweak these parts. So the classic thing that I think about when I talk about 3D printing is, for example, biomaterials. So if you're thinking about creating body parts that fit to someone's person, then obviously 3D printing is, you know, has to be considered as an answer. Because if I need a jaw replacement part, let's say I break my jaw and I need a plate that's exactly fitted to my bone shape, then obviously that will have to be 3D printed, right? That's certainly one way to do it. In applications such as jet engines, it's kind of like that, in that you do have, you know, this particular, for example, going back to my disc with blades, you know, these blades will be a particular shape, a particular height, a particular pitch, etc., and they're tailored for that specific disc, right? And so there'll be, say, 50 blades that you need in a jet engine. That's it, right? And you're not going to make that many jet engines, right? So you can see that this is an application. And these blades, by the way, you know, one of these blades, I think you can estimate the cost to be about $5,000, $10,000, something like that. So, you know, obviously, then you're talking about a low yield, high value part. So 3D printing might be something that could be used in the future. The problem as far as nickel-based superalloys is concerned, and the applications they're used in, is that we need really to control the microstructure really carefully to get the very advanced properties we require. So I mentioned that these blades are usually a single crystal. So that means you can essentially follow a row of atoms. You can hop from atom to atom in one direction. You can keep going up, hopping from one atom. They're all regularly, nicely aligned in rows, all the way from the bottom of the blade to the top of the blade. There is no defect, essentially, in these blades. And doing that with 3D printing at the moment is impossible, right? So we cannot quite do that at the moment. And who knows, maybe sometime in the future, there will be people that will develop a way for us to be able to do that. But where I think a lot of people are talking about 3D printing in jet engines is for effective repairs. So you might imagine that one of these blades or a component inside a jet engine gets chipped. You know, you get lots of things being sucked into engines that will eventually break parts off of these blades. And so you might want to be able to repair one of these blades rather than throwing it away and having to remanufacture the whole thing, because it's £5,000. So if it's a bit of a corner that you want to be able to touch up so that you perhaps retain a nice the shape you want, but that particular area is less problematic from the point of view of its properties, then you might be able to repair it using 3D printing. So that's one aspect. And then there is another aspect is the rapid prototyping. Say, for example, you're a company making jet engines, and you just come up with this new shape of blade that might just give you a better performance, and you want to be able to test that, and you want to be able to test that quickly. So again, 3D printing might be able to give you an answer in that space. So you might be able to manufacture parts that are prototype parts very quickly, very effectively using 3D printing.
It's interesting that you mentioned even like this maintenance part, because I know when I interned at GE Aviation, a significant portion of their revenue actually comes from like maintenance for their jet engines, even like potentially comparable to the sales of the jet engines themselves.
Some of these companies do not actually sell jet engines, they sell engine hours, right?
Oh, yeah.
So rather than, like, so for example, if you're buying, without mentioning specific manufacturer, but sometimes, you might not be able to buy the engine. So let's say you're a BA, you bought a plane, you might not have, you might not own the engine on that plane. You're just buying engine hours, and then the company will provide an engine that they will fit on the plane, and make sure that the engine runs. And if it breaks, they'll just replace the engine. But you're not buying the engine. The engine is not yours. They're just providing that engine and selling you engine hours. And I think I don't know whether GE does that, but Rolls-Royce I think does that. So that they will have different different business models depending on what they think they can, the most effective way of making money, I guess. Right. And maintaining these things are certainly a problem. And going back to the history of nickel-based superalloys, if we go back to the earliest jet engines, you were talking about jet engines that, as I said, weren't that efficient compared to the engines we have today. So they would only use, say 15, as I said, about 15 liters per passenger per 100 kilometers. And then you had to replace all the blades in them every 1,000 hours they run, right? So you can imagine, you had a comet, say, and you flew that comet for 1,000 hours. And after 1,000 hours, which is not that much, you had to replace every single bit in the jet engine, right? Yeah. Every single bit in the hottest part of the jet engine. But still, you have to open the whole engine, take it all apart, slot all these blades out of the discs and replace them with new ones, right? Nowadays, you're talking about tens of thousands of hours. Yeah.
Wow. So Alessandro, like talking about the business side of things, we have to talk about the costs as well. So I know that kind of limits its applications. So I was just wondering, what are the main challenges that superalloys need to overcome? And then I guess the second part of the question is, like, in jet engines, what is that range of costs for superalloys?
Well, that's interesting. I don't know the actual raw cost of the materials. I looked at, they fluctuate. That's the problem. And that's actually part of the problem of companies, is that oftentimes you don't just have a cost problem, but you have a problem that changes and it cannot really be predicted. So for example, I can make a few examples on these blades. In modern blades, one element that is significantly expensive for these blades is rhenium. Rhenium is added, probably you have about, something like 3 weight% added to a blade. It can be up to 5 weight% added to a blade, so not very much. But in terms of raw materials, it oftentimes makes more than half of the cost of all the elements, right? So you can imagine as a company making these blades, if you could remove rhenium altogether, you immediately make your raw materials half as expensive, right? So you can save significant money there. Also, in addition to make things even worse, when you add some of these elements to make this highest performing alloys, you often then have problems with manufacturing them, and so it is more expensive to manufacture them in a way that is leading to high yields. Sorry. So it can be something. It can be an additional cost at the start, but then that cost keeps piling higher and higher. Mm-hmm. And so obviously cost is a concern. The other one I mentioned is supply chain issues. So oftentimes the problem is not just cost, but the fact that the cost fluctuates because there is just one supplier that controls that supply, or because the supply is controlled by the refining of another element. So there are, in metallurgy, we mine all of these elements, and most of the time we mine ores that contain a range of different elements, and then we refine them to get the metals out of the ores. And sometimes the metals that are used in jet engines are actually byproducts of the refining of other elements that we refine. And so the cost will be largely driven by the manufacturing of something else. And so that might be a good thing in that it might be cheap, right? if you imagine an element that is a byproduct of something else, you're just using it, you weren't going to use it otherwise, it might be very cheap. But it means that, if that other product, that other element, suddenly the market for it disappears, then all of a sudden you don't have a stable supply chain. And also the other aspect is that you are then limited in the amount of that element you can use, because if you get to the roof of the amount of that production, then it might be difficult as a company to find other ways of getting that element, because the whole operation is based on making massive amounts of this initial element that someone else uses and you don't really need. So it's kind of complicated that way. And then you also have issues with where those elements are mined, how the conditions. So there might be issues with conflict, there might be ethical issues with perhaps child labor being employed in some of these mines, et cetera, et cetera. So it's quite complex. There might be national issues, i.e. You might have a situation where an element is only mined in a few places in the world, so there's only a few countries that control the supply of that particular element, and again, that might be a problem. So it's very complex. I think rhenium, which is the one I mentioned, is just a problem of it being high cost. Another element that is problematic in these alloys is ruthenium. Ruthenium it's got an unstable supply chain, I think, and so companies do not really like to use it. So in many cases, we know that we could use higher performing alloys that contain ruthenium, but companies actively don't pick those because they cannot have they're not confident in that supply chain to a way that they can rely on it to make their products. And so again, it goes back to the previous thing I mentioned. You can come up with the best composition in the world, but if the company decides it's not worthwhile, its bottom line to make it into a product, then it will never get that.
Yeah, that is a lot to take in, and just it seems like it's not even a technological problem. There's so many other problems associated with it that it's really going to be such a cross-functional problem to overcome. But yeah, thanks so much for talking to us today. We discussed several different applications of superalloys and how they've completely changed how we live. The idea of building from the bottom up and superalloys in general have garnered a lot of attention recently. So what advice would you give any material scientist who wants to pursue a career in this industry?
I think it's learn to code. Learn the computational aspects of things. So as much as I think traditionally material science is always seen as a fun discipline, because it's a lot of, at least metallurgy, the discipline I belong to, it's a lot about metal bashing and having fun with bits of material and trying to squeeze in properties out of them by doing fun things. But I think increasingly people use a lot more simulations, a lot more computation. And so if I had to go back to myself at the start of university, I would tell myself, learn to code quickly, because you're going to code a whole lot. And so now if I were to go back to myself again at the start of university, I'd probably say, this new thing of artificial intelligence and machine learning coming in, you definitely need to learn the nuts and bolts of these tools, because they are everyday tools. They're used quite a lot, and they're very effective. And the interesting thing about these tools is that you cannot just rely on a computer scientist to use it, right? We're not living in a world where material scientists and engineers will be basically removed from their positions and replaced with computer scientists that will just run an artificial intelligence that give you answers. I think the answer is to combine artificial intelligence and some of these modern tools with understanding and knowledge of the system and the material. And so as a material scientist, you need to know the material, you need to understand the material science. And I think you also need to understand some of these data tools, some of these simulation tools, because they're absolutely transformative. And as I said, the two combined is what's going to get us there. So you cannot just say, well, I'll go study computer science and forget about the theory and the science behind all this. That certainly is driving everything, but these tools are used, and we need to understand these tools in order to use them effectively.
Yeah, I would definitely say that when you do build models and other things, a lot of the first step is to first validate it with either your technological sense or your business sense. And if you don't know the theory, then that problem becomes insurmountable. And we can't tell the good ideas from the bad ideas, because the machine learning model will give you lots of ideas, and it's kind of up to us to discern which one is the best. But yeah, thank you so much for joining us today, Alessandro. It was great talking to you, and I learned a lot, and stuff about jet engines and superalloys is just really cool. And it seems like it will continue to play a huge part in how we live our lives.
No worries. Thank you for having me. Hopefully it was interesting for your audience as well.
Thank you for tuning in to this episode of the It's a Material World podcast. If you enjoyed the show, consider subscribing and hitting the like button down below. And if you'd like to support us on this journey or simply show off your love for MSc, we actually released merchandise. And if you'd like to check out more of the designs, visit itsamaterialworldpodcast.com/shop or use the link in the description. We'll see you soon. And in the meantime, go change the world.